If you are to go and look in the science hall and look at all the organic chemistry textbooks, you would find that there's a flux in definitions as to why 1,2 addition happens the way it does. So for the purpose of this research, I looked at the study of the addition of hydrogen halides to conjugated diene and alkene systems. A lot of words, but I can't explain. An alkene, for visual purposes, is right here. It has one carbon-carbon double bond. A diene, there's 3 types: conjugated, accumulated, and isolated. Have 2 carbon-carbon double bonds. Conjugated dienes are separated by 1 single carbon-carbon bond. However, accumulated dienes are 2 double bonds back to back, and an isolated diene is separated by more than 1 carbon-carbon single bond. So when you add a hydrogen halide, for our research we did HBr to this diene, you're going to have 2 different products that form. You're going to have a 1,2 and a 1,4 product. Your hydrogen is going to attack here, and it's going to form an allylic carbocation, which we can see here, which means the positive charge is resonating between these 3 different carbons. So like I said, your hydrogen attacks here, and then we have this allylic carbocation, which would be right here, your intermediate. And then your reaction has 2 processes it can follow. It can either go the 1,2 way, 1,2 product, and the 1,2 product can form, or the 1,4 product. The 1,2 product requires less energy, which could be in the form of an ice bath. So if you were to run your reaction on ice, you would have, it requires less energy, meaning it would follow this pathway, lower activation energy, however would have a less stable product. And like I said, this product, or this reaction happens very fast, your 1,2 product. However, your 1,4 product, if you were to run that on heat, for example, let's say at 66 degrees Celsius, you're adding heat, allowing, there's more energy for the system, so it can follow this red line here, which has a higher activation energy, and the 1,4 product is more stable. And that is the thermodynamic product, which is very well understood. However, in 1979, Dr. Eric Nordlander challenged this idea of the activation energies by creating a symmetric allylic carbocation intermediate using 1,3-butadiene, which means he had a molecule and the intermediate was symmetric. So at that point, you eliminate the difference between these activation energies between the 1,2 and the 1,4, and they're the exact same. So you would assume that 50% goes to 1,2 and 50% goes to 1,4. However, that's not what he saw. He saw that the 1,2 product dominated over the 1,4 product, meaning that he could accredit the ion pair, later to be known as the proximity effect, which means that instead of adding to the 4th carbon, it's going to add to the 2nd carbon. The chloride ion is going to add to the 2nd carbon because it's closer. So your hydrogen's going to attack that 1st carbon, your your halide is going to attack the 2nd carbon just because it's closer. That's the only thing that's influencing the system. So right now we have this flux between the activation energies and the proximity effect. So for our research, I looked at the addition of hydrogen halides to conjugated dienes and alkene systems. I had a variety, and we hypothesized that there will be not one or the other that's the reason as to why this happens, but a combination of both. And we hope to someday down the road be able to change this in textbooks. That way students are learning the truth about how 1,2 addition occurs. So we use, like I said, a variety of alkenes. We use 2,5-dimethyl 2,4-hexadiene. We use cyclohexene. We use cyclohexene 1-methyl cyclohexene. And then we mix those with our hydrogen halide, which was, for us, we used hydrogen bromine at different ratios, temperatures, and then reaction times. We used different washes to wash this after we had created our product, and then we used NMR, carbon-13 NMR, and proton NMR, as well as gas chromatography. As you can see here in our proton NMR, this is our chloroform peak, which is very big for what we wanted, and this is around here was where our alkene was, but right here is what we believe is our product peaks. However, these peaks are very small, which inhibited us from furthering our research. So we took a step back, and then we started looking at alkenes. So here is a gas chromatograph of cyclohexene, and then this is just where cyclohexene came off in the gas chromatograph. However, when we kept running samples, parameters were changed in the middle, and we were not running our gas chromatography for as long as it needed to be at the correct temperatures, which meant we weren't seeing the actual products in our graphs. So at that, we were sort of left at a standstill, and products had been dried out, and right now, to sort of further our analysis of this research, we need to go back and we need to redo the reactions, hoping for higher yields, and we need to redo all of our GC data, which we have right here, you can see, which is very small, but it shows all the ratios, temperatures, and reaction times. We need to redo these, allowing us to be able to see the whole graph of our GC, which will be able to allow us to analyze our data in the future. So right now we have high ether peaks, high chloroform peaks, which are our washes, and we are not seeing our product peaks as we wish to be. So right now we're inconclusive, however we do think we are on the verge.